Okay, so something that we should think about for inductors, capacitors, and resistances is, are they synchronous or not? So we talked before, the resistor doesn't really care much about when the voltage is doing what the voltage does, right? And let's say I'll make orange the current. If this is the current in a system as it's oscillating, then by V equals IR, we want to know what's the voltage on the resistor. It would be in lockstep, right? They're synchronous. So this one's all kind of in sync. There's no phase difference between the two. It's just as time goes on, this is the voltage and this is the current, VR and I guess I. And if we really wanted to kind of say, what is that? I guess V is equal to IR. And this is V on the resistor by Ohm's law. Okay, our other two. Let's say for a moment that the current in the capacitor looks like this. And I offset a little bit to use a cosine just because it kind of makes the picture a little easier to see. This is the current behavior in the capacitor, right? Which, if the current's flowing at its max value, then that means the charge on the capacitor is 0. And therefore, by what? Q is equal to C V capacitor? Well, that means the voltage is also 0. As the current dies off and fills up, the capacitor fills up, it kills off the current, and then we have this kind of behavior. If we're pulling the charge out like this, well, then we should have a negative current flow in the backwards direction. And this cycle kind of seems to repeat like this. And these are off by a quarter cycle, right? This is a 90-degree difference. Which one happened first? If this is time equals 0, immediately I'm at maximum current, and then later on I reach maximum charge or voltage. So it seems like in this case, the current leads the voltage on the capacitor. Or we could say that, the voltage on the capacitor lags behind the current. It's just a little bit later. If we did the same thing for the inductor, and I guess let's start out with just some formula for or some function for the current. Let's see, that's the capacitor. The inductor, how does it behave? We know VL is negative L di dt. And we say negative because that's Lenz's law. This is all Faraday's law stuff, talking about the rate of change of the current going through the inductor. But it's going to fight back, and back means negative sign. So let's think about that. The derivative of these currents, here the derivative is kind of high, right? Because it's at its steepest. Here the derivative is 0, so maybe it'd be better to think about these two zeros here. Well, I think I screwed myself up. In this, I don't know really what's going on here. This happens every single time I teach this. I always get bogged down in one of these details. So what should have happened is this. It's known, you'll see it in the lab, it happens all the time. The voltage is in fact ahead, or it happens first. Time goes forward. Here we have our V peak. Here we have our I peak later. You'll have to take my word for this or go back and try to figure out the derivation. There's a mistake somewhere. VL leads the current. So these are just the rules for these devices. They unfortunately are not synchronous with each other. And that makes things a little bit complicated. And we'll have to talk about why kind of in one of the next few slides. When we do this, we just know V and I have no phase separation angle. They're the same. So this is in sync. The current leads the EMF if the device is capacitive. And the current leads the EMF leads the current if the device is inductive. This is somewhere in your book. I'm not sure where, but I do know it's in every book. It's either in a footnote or it's in one of the example problems. It's in the blue boxes that you didn't look at. This mnemonic will help you out all the time. Whenever you're in doubt, ask Eli the Iceman to help you figure out a capacitive or an inductive circuit. If your EMF happens first before your current, then the device is inductive. If your EMF lags behind or happens after the current, then the device is capacitive. And I am so sure, because I met the guy, I really, really know that Eli is the Iceman. In fact, I'm positive that Eli is the Iceman. So I'm going to modify this and say Eli is positively the Iceman. That gives us even more evidence. This phase angle, if it's greater than 0 or it's positive, it's inductive. And if it's not, then it's not. So this little mnemonic device, Eli the Iceman, is the key to cracking a lot of the issues that we have with AC circuits. Okay? The lead lag behavior, the phase angle behavior, and all this other stuff. It's worthwhile for us to just know that the system doesn't have to be purely inductive or capacitive, right? So in this case, if it was just a straight capacitor by itself, it would have a phase angle of 90 degrees. Actually, negative 90 degrees, because it's a negative phase angle. If it's inductive, we know that the separation between these two is exact. It's a perfect 90 degrees because it's a pure circuit. But I can, of course, have an L and a C put together in some way. And the circuit is determined to be either inductive or capacitive by its phase angle. So what are things? Okay, hope we can still hear. I ran out of storage space on the phone. I think we were asking, how can we tell if a circuit is inductive or capacitive, if it's somewhere kind of in between these two options? So if the circuit is inductive more than it is capacitive, what evidence do we have to help us find this? Well, the first one is the EMF happens before the current in the cycle, if you can see it. So just check it out. Say, is this an ELI circuit or not? If you happen to know some of the math, like the cosine function or the sine function, and you have access to the phase angle, then we know that that would be a positive case. And another way that we can to do it is by direct inspection. If you've got more than one component, which one dominates? If your inductive reactance is literally more ohms than the capacitive part, well, then the circuit is more inductive. It's got more inductive properties than it has capacitive. So let's look at the other case. How do we determine if it's capacitive? Well, we can look at the trace behavior. Is it ICE or ELI? You can look at the phase angle and see, is it negative? And I bet you can predict this part. Do a direct comparison or an inspection. If it is more capacitive, then the circuit is capacitive, right? So these things are what will get you through identifying is a blended circuit that's a little bit capacitive or inductive. You know, how do we find its overall behavior? So I think the only thing left to do in this discussion is say, how do we tie it all together and put capacitors, inductors, maybe even resistors, all these components, how do we put them into a circuit and then find out, hey, what is the overall reactance or resistance or whatever you want to call it for the entire thing? And that is going to be a big conversation.